2.5 million years of light travel away, a monster is growing larger. Scientists just measured something impossible. The Andromeda Galaxy is not the size we thought. It is 6 times wider than the full moon in your sky right now, but you cannot see it. Its invisible halo stretches halfway to Earth, already touching our galaxy. 1 trillion stars spin inside a disk 220,000 light-years wide, surrounded by a gas cloud extending 2 million light-years in some directions. The collision everyone predicted might not happen at all, or it might tear both galaxies apart. If you enjoy learning about the cosmos, consider subscribing. We are about to explore the largest structure you cannot see. Prepare yourselves. We begin. Stand outside on a clear autumn night and look up. Find the faint smudge in the constellation named for a princess chained to a rock. That blur, you barely notice, spans 6 times the width of the full moon. Your eyes deceive you because Andromeda glows too dim for your vision to register its true scale. If this galaxy burned just slightly brighter, it would dominate the entire sky like a cosmic rainbow stretching from horizon to horizon. Astronomers have known about this nearby giant for over 1,000 years. Ancient Persian scholar Abd al-Rahman al-Sufi recorded it in the year 964, calling it a small cloud. For centuries, observers assumed they were looking at a nebula, a gas cloud inside our own galaxy. They had no idea they were staring at an entirely separate island of stars containing 1 trillion burning spheres, each one potentially hosting worlds of its own. The breakthrough came when scientists measured not just brightness, but angular size. Angular size tells us how much of the sky an object covers from our perspective. The moon spans roughly half a degree. A right angle contains 90 degrees. The Big Dipper stretches about 25 degrees across the sky. Andromeda, when properly measured with sensitive instruments, covers more than 3 degrees in its longest dimension. This creates a strange paradox. Something 6 times wider than the moon should be impossible to miss, yet most people have never seen it. The reason lies in surface brightness. Andromeda spreads its light across such a vast area that each tiny portion of sky it occupies glows incredibly faint. Your eye needs concentrated light to trigger recognition. Spread that same amount of light over 6 times the area, and it vanishes into the background glow of the night sky. Researchers using specialized cameras and long exposure times revealed what our eyes cannot perceive. They captured photons arriving from this distant galaxy over hours, building up an image that shows the true extent of its glowing disk. The core appears bright and compact, exactly what naked eye observers see, but extending outward in elegant spiral arms, fainter and fainter regions of starlight trace a structure so massive it challenges comprehension. Think about what this means for scale. The moon sits only 240,000 miles away, close enough that 12 humans have walked on its surface. Andromeda lies 2.5 million light-years distant. A light-year equals nearly 6 trillion miles. Multiply that by 2.5 million. The galaxy appears 6 times wider than the moon, despite being billions of times farther away. The actual physical size must be staggering beyond imagination. Scientists compare angular measurements to a simple test. Hold a basketball at arm's length. That circle covers about the same angular size as 2 full moons. Andromeda's visible disk would require you to hold 12 basketballs side by side to match its span across the sky. Yet, from our perspective, this entire structure compresses into a blur most people never notice, lost in the vast darkness between more obvious stars. But this visible disk represents only the beginning of the story. What astronomers recently discovered makes even this impressive measurement seem small. Chapter 2: The Visible Disk Measurement Breakthrough. For decades, astronomy textbooks stated with confidence that Andromeda measured roughly 70,000 to 80,000 light-years in diameter. Scientists calculated this number by identifying where the visible starlight faded below detectable levels. They assumed anything beyond that edge was simply empty space, the transition zone between galaxy and void. They were catastrophically wrong. The error persisted because measuring galaxy size is far more complicated than it appears. Unlike a planet with a solid surface, galaxies have no clear boundary. Stars thin out gradually as you move from the dense core toward the outer regions. At some point, the starlight becomes so faint that telescopes can no longer distinguish it from the background glow of space itself. That detection limit became, by default, the assumed edge of the galaxy. Advanced telescopes changed everything. The Keck Observatory in Hawaii, equipped with massive mirrors and incredibly sensitive instruments, began studying individual stars far beyond what anyone thought was Andromeda's edge. Researchers led by astronomer Scott Chapman analyzed the motion of roughly 3,000 stars scattered in what previous observers had dismissed as the halo region. These stars were thought to be random stragglers, remnants of smaller galaxies that Andromeda had consumed long ago. The motion measurements told a different story entirely. Each star moves through space, following the gravitational pull of nearby matter. By measuring how fast each star travels and in what direction, scientists can determine whether it orbits the galaxy's center or simply drifts randomly through space. The Keck team discovered something shocking. These supposedly stray stars were not wandering at all. They orbited in the same plane as the main disk, rotating around the galactic center in organized patterns. This revelation forced a complete recalculation. If these outer stars shared the organized rotation of the inner disk, they must be part of that disk, not separate from it. The spiral structure of Andromeda extends far beyond where its light fades from view. The actual stellar disk spans approximately 220,000 light-years from edge to edge, making it 3 times larger than previously believed. To grasp this scale, consider our own galaxy. The Milky Way measures roughly 100,000 light-years across. Scientists long assumed Andromeda was only slightly larger, perhaps by 20 or 30%. The new measurements revealed that Andromeda absolutely dwarfs our home galaxy. Its disk covers more than twice the area. The volume of space it occupies multiplies accordingly. This is not a marginal difference. This represents a fundamental misunderstanding of how large spiral galaxies can grow. The outer regions of this extended disk look nothing like the bright, organized spiral arms near the core. Instead, the stellar distribution appears clumpy and irregular, with stars gathered in loose associations rather than smooth streams. This strange structure provided additional clues about Andromeda's violent past. Computer simulations showed that this messy outer disk could only form through collisions. Smaller satellite galaxies must have slammed into Andromeda billions of years ago, their stars scattered and absorbed into an extended, turbulent disk. The implications ripple through multiple fields of astronomy. Galaxy formation models, star population statistics, mass estimates, and dark matter calculations all depended on the old, incorrect size measurement. Every one of these models now requires revision. The true Andromeda is larger, more massive, and more complex than decades of research had suggested. Yet even this corrected measurement captures only what glows bright enough to detect. The real boundary lies much, much farther out. Chapter 3. The invisible halo that changes everything. Galaxies do not end where their stars fade. Every spiral galaxy floats inside an enormous envelope of gas, an atmosphere that extends far beyond the visible disk. Astronomers call this structure the circumgalactic medium, or halo. For Andromeda, this invisible shell rewrites everything we thought we knew about galactic scale. The halo consists primarily of hydrogen and helium, the simplest and most abundant elements in the universe. But unlike the dense gas clouds where stars form, this halo gas exists in an extremely rarefied state. Imagine taking a single sugar cube and spreading its molecules across a volume larger than Earth. That gives you some sense of how thin this gas truly is. In most of space, you might find a few atoms per cubic centimeter. In the halo, the density drops to less than 1 atom per 10 cubic centimeters. This extreme thinness makes the halo effectively invisible. It does not shine on its own. It does not block light from objects behind it. It exists as a ghost, detectable only through the most sophisticated techniques available to modern astronomy. For years, scientists suspected such halos existed, but had no way to study them in detail. The breakthrough came from an unexpected source. Quasars provided the key. These objects rank among the brightest phenomena in the universe. They form when matter spirals into supermassive black holes at the centers of distant galaxies, heating to millions of degrees and blasting out radiation across all wavelengths. Some quasars shine so brilliantly they outshine entire galaxies, remaining visible even from billions of light-years away. More importantly, their light travels through space for eons before reaching Earth, passing through any gas clouds that happen to lie along the way. Gas absorbs light, but only at very specific wavelengths corresponding to the atoms present. When quasar light passes through a halo, atoms of hydrogen, oxygen, carbon, and silicon each steal photons at their characteristic wavelengths. By splitting the incoming light into a spectrum and looking for these absorption features, astronomers can detect gas clouds that would otherwise remain completely invisible. It is like shining a flashlight through fog. You cannot see the fog droplets directly, but you notice how they dim and scatter the beam. The Hubble Space Telescope's Cosmic Origins spectrograph turned this technique into a precision tool. Researchers identified 43 quasars positioned behind Andromeda from our point of view. Each quasar acts as a backlight, illuminating whatever gas lies between it and Earth. By studying how the light from each quasar changed, scientists mapped the three-dimensional structure of Andromeda's halo in unprecedented detail. The results shocked everyone. Previous estimates, based on limited data from just 6 quasars, suggested the halo might extend a few 100,000 light-years from the galaxy. The comprehensive mapping revealed the truth. The halo stretches 1.3 million light-years in the direction of our own galaxy. That represents roughly half the distance from Andromeda to the Milky Way. In other directions, the halo extends even farther, reaching 2 million light-years from the galactic center in certain directions. If human eyes could see this halo, it would dominate the night sky. The visible portion would span an area 3 times the width of the Big Dipper, making it easily the largest feature in the heavens. Every time you looked up on a clear night, this immense, glowing sphere would stretch across massive sections of the sky. But the gas glows too faint, and our eyes lack the sensitivity to register such diffuse light. The halo contains an almost unbelievable amount of matter. By measuring absorption strength at different distances from the galaxy, researchers calculated the total mass of gas suspended in this enormous volume. The halo holds at least half as much mass as all the stars in Andromeda's disk combined. That means if Andromeda contains 1 trillion stars, the surrounding gas possesses mass equivalent to 500 billion stellar masses worth of material. This discovery forces astronomers to reconsider what we mean when we talk about a galaxy's size. The visible disk spans 220,000 light-years, but the true gravitational sphere of influence, the region where Andromeda's gravity dominates and shapes the motion of matter, extends 10 times farther. By any reasonable definition, Andromeda is vastly larger than traditional measurements suggested. But the most unsettling revelation was still to come. Chapter 4. The 2 million light-year boundary. The halo does not extend uniformly in all directions. Like a balloon squeezed unevenly, Andromeda's gaseous envelope stretches farther in some directions than others. In certain regions of space, tendrils of hot, ionized gas reach outward to 2 million light-years from the galactic center. This represents the absolute outer limit of Andromeda's direct influence, the frontier where its gravity and expelled material finally disperse into intergalactic space. Scientists discovered this asymmetry by carefully analyzing absorption patterns from all 43 background quasars. Each quasar samples a different line of sight through the halo. Some pass through regions closer to the galactic disk, others through zones above and below the plane of rotation. By comparing absorption strength and gas velocity for each line of sight, researchers built a 3-dimensional model showing how halo density and temperature vary with position. The extended regions correspond to areas where supernovae have blasted material outward with tremendous force. When massive stars exhaust their fuel and explode, they do not simply destroy themselves. They propel surrounding gas away from the explosion site at speeds exceeding thousands of kilometers per second. In a dense environment like the galactic disk, this ejected material crashes into nearby gas clouds and slows down relatively quickly. But some of it shoots upward or downward, perpendicular to the disk, where very little material exists to stop it. This escaping gas carries enormous energy. It stays hot, with temperatures reaching millions of degrees. At these temperatures, electrons strip away from atoms entirely, creating a plasma of bare nuclei and free electrons. This ionized gas spreads outward, driven by its own thermal pressure and the continued push from subsequent supernova explosions. Over billions of years, plume after plume of expelled material builds up an extended halo reaching far into intergalactic space. The 2 million light-year boundary marks where this process finally exhausts itself. At that distance, the expelled gas has cooled enough and spread thin enough that it merges with the general intergalactic medium filling the space between galaxies. Andromeda's gravitational pull, while still present, becomes too weak to hold this distant material in orbit. The gas either escapes entirely or settles into the vast reservoir of matter surrounding galaxy clusters. This outer halo contains the fossil record of Andromeda's entire life history. Every generation of massive stars that lived and died contributed to this cloud. The chemical composition reveals which elements formed in stellar cores and which came from supernova explosions. Variations in density trace ancient collision events, times when smaller galaxies crashed into Andromeda and disturbed the halo structure. Temperature differences map where star formation was most active in different eras. Measuring out to 2 million light-years also reveals another crucial fact. The distance from Andromeda to the Milky Way is approximately 2.5 million light-years. If Andromeda's halo extends 2 million light-years in some directions, and if our galaxy has a similar halo extending outward, then simple arithmetic shows the two halos must overlap. There should be a region of space where gas from both galaxies intermingles, a cosmic boundary zone where the influence of each galaxy meets and interacts. This realization led researchers to a startling conclusion that nobody had anticipated. They were not looking at two separate galaxies approaching each other through empty space. They were observing two galaxies whose outer atmospheres had already made contact. Chapter 5. The Halo-Touching Revelation. The collision has already begun. Not the dramatic smashing of stellar disks that will come billions of years from now, but something more subtle and profound. The diffuse outer layers of both galaxies are mixing right now, creating a cosmic interaction zone where matter from Andromeda and matter from the Milky Way press against each other in the darkness of intergalactic space. Scientists verified this through careful analysis of gas velocities in the outer regions of Andromeda's halo. When two gas clouds approach each other, they do not simply pass through like ghosts. They compress, heat up, and transfer momentum. The collision zone should show distinctive signatures in both temperature and motion patterns. Researchers found exactly that. At distances around 1 million light-years from Andromeda, right at the halfway point to the Milky Way, the halo gas shows characteristics indicating it is being compressed by external pressure. This external pressure can only come from one source. The Milky Way's own halo, extending outward from our galaxy, pushes back against the advancing gas from Andromeda. Like two spheres of influence slowly pressing together, the halos create a boundary layer where compression heats the gas and slows its motion. This interaction zone may span hundreds of thousands of light-years, a vast region where the properties of intergalactic space differ from the surrounding medium. The implications reach far beyond simple measurements. When galaxy halos touch and begin mixing, they exchange matter. Gas expelled from supernovae in Andromeda may eventually rain down onto the Milky Way, providing fresh material for future star formation. Conversely, gas blown out of our galaxy might cross the boundary and join Andromeda's reservoir. Over millions of years, this slow transfer could move significant amounts of mass between the two systems. This process also explains some puzzling observations about the local intergalactic medium. Astronomers have detected clouds of gas in the space between galaxies that seem too hot and too enriched with heavy elements to be primordial material left over from the Big Bang. These clouds might represent debris from the halos of nearby galaxies, mixed and stirred by their mutual gravitational influence. Andromeda and the Milky Way contribute to this local cosmic soup, seasoning intergalactic space with the products of stellar evolution. The halo interaction also affects how we think about galaxy mergers. Traditional models assumed galaxies approached as distinct objects, remaining separate until their stellar disks finally collided. The halo studies reveal a different picture. Galaxies begin influencing each other far earlier, through the interaction of their extended gaseous atmospheres. By the time the visible portions touch, the galaxies have already been gravitationally and chemically connected for millions or billions of years. Scientists now recognize they are witnessing the very earliest stage of a merger process. The word collision suggests a sudden, violent impact. Reality proceeds more gradually. First, the halos touch and begin mixing. Then, over hundreds of millions of years, gravitational attraction pulls the galaxies closer. The halos compress further, heating up and possibly triggering bursts of star formation as gas clouds collide. Finally, billions of years from now, the stellar disks themselves interpenetrate, and the galaxies lose their separate identities. We stand at the beginning of this timeline, observing the first tentative contact between two galactic giants. The stars remain separated by over 2 million light-years. But the atmospheres surrounding those stars have already bridged the gap. Andromeda and the Milky Way are touching. Even if you cannot see it, what surprised researchers even more was discovering that this touching halo has structure. Chapter 6. The double shell structure mystery. The halo is not uniform. It possesses a distinct layered architecture, with two separate shells nested inside each other like Russian dolls. Each shell has different properties, different temperatures, different chemical compositions, and different velocity patterns. Understanding why this double structure exists reveals fundamental truths about how galaxies evolve. The inner shell extends roughly 500,000 light-years from the galactic center. Scientists describe this region as complex and dynamic. Gas velocities vary dramatically from place to place. Some regions move rapidly outward, pushed by recent supernova explosions. Other areas show infall, material falling back toward the galaxy under gravitational attraction. Temperature fluctuates across a wide range. Chemical abundances change noticeably from one zone to another. This inner shell bears the direct influence of activity in the galactic disk. When massive stars explode, their blast waves reach the inner halo within a few million years. Fresh supernova debris, rich in elements like oxygen, carbon, and silicon, mixes into the pre-existing gas. Multiple overlapping bubbles of hot, expanding material create a churning, turbulent environment. Think of boiling water, with rising plumes of hot liquid and sinking streams of cooler material creating constant motion and mixing. The outer shell tells a very different story. Beginning around 500,000 light-years and extending all the way to the 2 million light-year boundary, this region appears smooth and hot. Temperature stays consistently high, around 2 million degrees. Gas velocities show far less variation, with most of the halo moving at similar speeds. Chemical abundances remain more uniform across large distances. Scientists interpret this smoother outer shell as older, more settled material. The turbulent processes that dominate the inner shell have had time to even out in the outer regions. Gas that was expelled hundreds of millions or billions of years ago has cooled, spread, and mixed thoroughly. The outer halo represents a more quiescent phase of galactic evolution, when the violence of recent star formation fades and gravity begins pulling material back toward the galaxy for future recycling. The boundary between these two shells is not sharp. Instead, properties transition gradually over a zone, perhaps 100,000 light-years thick. This transition region shows intermediate characteristics, suggesting ongoing exchange between the shells. Gas from the inner shell continues flowing outward, joining the outer halo. Meanwhile, cooling gas in the outer regions loses energy and pressure, allowing gravity to pull it back down into the inner shell. The existence of this layered structure was not predicted by theoretical models. Computer simulations of galaxy formation generally produce halos with more uniform properties. The observed complexity suggests that our understanding of supernova feedback remains incomplete. How exactly do exploding stars inject energy into the halo? How efficiently does that energy propagate outward? How much material escapes completely versus falling back for recycling? These questions lack definitive answers. Some of the most intriguing clues come from measuring heavy element abundances in both shells. Elements heavier than hydrogen and helium can only form inside stars or during supernova explosions. Their presence in the halo proves the gas once resided in the galactic disk, where stars formed and died. By measuring the relative amounts of different elements, scientists can infer which types of supernovae contributed most to the enrichment. The inner shell shows clear signs of contamination from recent supernovae. Oxygen and silicon appear in higher proportions than in the outer shell. This matches expectations, since these elements form preferentially in massive stars that explode as core collapse supernovae. The outer shell shows a slightly different pattern, with more iron relative to other elements. Iron comes primarily from type Ia supernovae, which occur when white dwarf stars explode after accreting material from companions. These explosions happen more gradually over time, suggesting the outer halo contains contributions from many generations of stellar evolution. The double shell structure also affects predictions about the future. As Andromeda and the Milky Way approach, their halos will not merge smoothly. Instead, the complex inner shells will collide first, creating a zone of enhanced turbulence and possibly triggering new waves of star formation. The outer shells will compress against each other, heating up further and potentially driving some gas to escape velocities where it flies away from both galaxies entirely. This structure makes the approaching merger far more complicated than a simple combining of two spheres. We are watching the beginning of an interaction involving multiple layers, each with its own behavior and its own timeline for integration. But the halo represents only one component of Andromeda's vast mass. Chapter 7. The Trillion Star Population. 1 trillion stars. The number is so large it loses meaning. If you counted 1 star per second without stopping, reaching 1 trillion would require 31,000 years. Andromeda contains enough stars to give every person who has ever lived on Earth more than 100 billion stars each. This population dwarfs our own galaxy by a factor of roughly 3 to 1. These stars are not evenly distributed. The density varies by a factor of millions from the dense core to the sparse outer regions. In the central bulge, stars pack together so tightly that typical distances between them shrink to a few light weeks instead of light years. If you lived on a planet orbiting a star in that region, your night sky would blaze with thousands of stars brighter than Venus appears from Earth. The combined glow would cast clear shadows at midnight, move outward into the spiral arms, and the stellar density drops, but remains far higher than the space around our own location in the Milky Way. Andromeda's spiral structure contains massive star formation regions, stellar nurseries where gas clouds collapse to birth new stars continuously. These regions blaze blue and white from the light of young, hot stars. Each active star formation zone might create thousands of new stars over just a few million years. The spiral arms themselves trace density waves moving through the galactic disk. These waves do not consist of stars flowing along like water in a river. Instead, the wave represents a region where gravity temporarily increases star density as stars in their individual orbits bunch together. Imagine cars on a highway encountering a slow zone. The cars compress together, creating a region of high density, but then spread out again as they pass through. Spiral arms work similarly, with stars spending part of their orbital time in the arm and part of their time in the gaps between arms. Between the arms, the stellar population thins to resemble our local neighborhood. Here, older stars dominate, having formed billions of years ago and gradually drifted away from their birth sites. These stars shine yellow and red, cooler and dimmer than the blue giants in the star formation zones. They represent the bulk of Andromeda's stellar mass, the long-lived inhabitants that will continue burning for trillions of years after the brief, bright young stars have exhausted their fuel and died. Andromeda also contains hundreds of billions of failed stars, brown dwarfs too small to ignite fusion in their cores. These objects formed the same way as stars, from collapsing gas clouds, but never accumulated enough mass to start hydrogen burning. They glow dimly in infrared light, gradually cooling over billions of years. Though they contribute little to the galaxy's luminosity, their mass still matters for calculating total galactic mass and gravitational dynamics. The variety of stellar types mirrors the population of our own galaxy. Red dwarfs, small stars burning slowly, probably outnumber all other types combined. These tiny stars will outlive everything else, continuing to shine faintly for trillions of years after stars like our own fade away. At the other extreme, massive blue supergiants burn through their fuel in mere millions of years, ending their lives in spectacular supernova explosions that enrich the galaxy with heavy elements. Binary stars appear throughout the galaxy, systems where two stars orbit each other. In some cases, these binaries orbit so close that material flows from one star to the other, creating bizarre systems where a white dwarf cannibalizes its companion or a neutron star heats surrounding gas to millions of degrees. These interacting binaries produce X-rays, gamma rays, and sometimes dramatic outbursts visible across millions of light-years. Planet systems likely orbit most of these stars. If the ratio of planets to stars in Andromeda matches what we observe in our own galaxy, trillions of worlds circle those distant suns. Rocky planets, gas giants, ice worlds, and stranger configurations we have not yet imagined. On some unknown fraction of those worlds, conditions might permit the chemistry that leads to life. Across a trillion stars, even vanishingly unlikely events become probable. Intelligent civilizations might look out at their own night sky and wonder about the faint smudge they call the Milky Way. Measuring this trillion-star population required decades of careful observation. Scientists cannot count individual stars in Andromeda's core, where millions pack into regions smaller than the distance between our own star and its nearest neighbor. Instead, they measure total light output and divide by average stellar brightness to estimate total star count. In the outer regions, where stars separate enough to resolve individually, direct counting becomes possible, but remains time-consuming. The Hubble Space Telescope dedicated years to mapping Andromeda in unprecedented detail. The project, called PHAT, Panchromatic Hubble Andromeda Treasury, captured over 600 separate images that researchers stitched together into a massive mosaic. This portrait resolved more than 100 million individual stars, though that still represents only 10% of the galaxy's total population. The remaining 90% either hide in the crowded core or scatter through the vast outer halo beyond Hubble's detection limit. This stellar census becomes crucial for understanding the galaxy's future evolution. How rapidly is star formation proceeding now compared to billions of years ago? How much gas remains for future star formation? These questions require knowing both how many stars currently exist and how much mass each generation of stars locks away versus returning to the interstellar medium. The trillion-star population represents the end product of over 10 billion years of galactic evolution, a snapshot of Andromeda's current state. But counting stars represents only one way to measure galactic size. Another method looked at motion. Chapter 8. The Stellar Disk Motion Discovery. 3,000 stars changed everything. That modest sample, carefully selected and meticulously observed, revealed that astronomers had fundamentally misunderstood where Andromeda's disk ends and its halo begins. The key was not how bright these stars shone, but how they moved. Stars in a rotating disk follow predictable patterns. They orbit the galactic center in roughly circular paths, all moving in the same direction around the rotation axis. Like runners on a circular track, they maintain orderly motion even as their speeds vary depending on distance from the center. Stars in the halo behave completely differently. They move on elliptical or even chaotic orbits, plunging through the disk at various angles. Their motions appear random when averaged together, with no preferred direction. The team from the California Institute of Technology and the observatories of the Carnegie Institution used the Keck telescopes to measure something called radial velocity for each target star. Radial velocity tells you how fast an object moves toward or away from you, but reveals nothing about sideways motion. This might seem limiting, but for a galaxy as nearby and well-studied as Andromeda, knowing the radial velocity is enough. Here is why that works. Andromeda is tilted relative to our line of sight, seen almost edge-on but not quite. One edge of the galaxy tilts toward us, the other away. Stars on the approaching side show blue-shifted light, wavelengths compressed by the Doppler effect. Stars on the receding side show red-shifted light, wavelengths stretched by their motion away from us. Stars in the middle, moving perpendicular to our line of sight, show no Doppler shift at all. If a star orbits in the galactic disk, its radial velocity depends entirely on its position in that disk. Stars on one side all move toward us at similar speeds. Stars on the opposite side all move away at similar speeds. The pattern of velocities across the galaxy traces out a beautiful, symmetric curve called a rotation curve. By contrast, halo stars show radial velocities scattered all over the place, with no correlation to position, because their orbits point every which way. The California team measured radial velocities for 3,000 stars in the outer regions of Andromeda, far beyond where previous studies assumed the disk ended. They expected to find random halo-like velocities. Instead, they found the signature of rotation. These supposedly stray stars moved in organized patterns, all participating in the galaxy-wide rotation. This could mean only one thing. These stars were not halo members wandering randomly through space. They belonged to the disk itself. This discovery required extraordinary measurement precision. The stars in question shine faintly, their light diluted by immense distance. Measuring Doppler shifts accurate enough to detect orbital motion demanded using spectrographs on the largest telescopes available. The Keck Observatory's 10-meter mirrors collect enough light to create detailed spectra even for these dim targets. Each spectrum shows absorption lines created by elements in the star's atmosphere. Measuring tiny shifts in these line positions reveals velocity differences as small as a few kilometers per second. The team worked systematically, observing stars scattered across a wide area around Andromeda. Some regions showed clear disk rotation, confirming those stars belonged to the extended disk. Other regions showed mixed results, possibly indicating a transition zone where disk and halo overlap. The most distant regions, beyond about 110,000 light-years from the center, showed predominantly random velocities, finally marking the true boundary between disk and halo. Plotting all 3,000 velocity measurements on a map of Andromeda revealed striking patterns. The rotation curve extended much farther than anyone expected, maintaining significant orbital velocity out to distances where no visible structure appeared in photographs. This proved the disk continues outward as a very low surface brightness feature, too faint to see directly, but still gravitationally bound and rotating with the rest of the galaxy. The extended disk also showed another unusual feature. Its rotation velocity did not decrease smoothly with distance from the center. Instead, the curve showed bumps and wiggles, regions where stars moved faster or slower than predicted by simple models. These velocity variations trace the influence of dark matter, the invisible mass that provides most of Andromeda's gravitational pull. By mapping how rotation speed changes with position, scientists can infer how dark matter distributes itself through and around the galaxy. This discovery method demonstrates a powerful principle in astronomy. Sometimes the most important information comes not from what you see, but from how things move. Andromeda's true size remained hidden until astronomers stopped relying solely on images and started measuring velocities. The galaxy turned out to be much larger than it appeared because its outer regions shine too faintly to detect through normal imaging, but move obviously enough to reveal themselves through spectroscopy. The irregular structure of this extended disk also told a story about collisions. Computer simulations showed that smooth, orderly disks do not naturally produce the clumpy, asymmetric features observed in Andromeda's outer regions. Something must have disturbed the outer disk, stirring up the stars and creating irregularities. The most likely culprit involves smaller galaxies crashing into Andromeda in its past. These past collisions left evidence throughout the galaxy. The motion measurements provided one crucial piece of that evidence. Chapter 9. The Quasar Mapping Technique. 43 points of light, each billions of light-years beyond Andromeda, provided the tools to map an invisible structure. Without these brilliant beacons scattered across the sky behind the galaxy, the halo would remain completely undetectable. Their light, traveling for eons across the universe, creates lines of sight that pierce through Andromeda's gaseous atmosphere, carrying information about every atom they encounter. Quasars shine because matter spirals into supermassive black holes at the centers of distant galaxies. As gas clouds fall toward the black hole, friction and compression heat them to temperatures exceeding millions of degrees. At these temperatures, matter radiates across the entire electromagnetic spectrum, from radio waves to X-rays. Some quasars shine so bright they outshine their entire host galaxy, making them visible even from distances where normal galaxies fade beyond detection. Finding 43 suitable quasars required extensive previous surveys of the sky. Astronomers cannot simply look behind Andromeda and spot quasars easily. The galaxy itself blocks much of the view, and many objects that appear to be background quasars might actually be foreground stars in our own galaxy or other nearby galaxies in the local group. Confirming each candidate requires measuring its spectrum and showing characteristic features that only quasars produce. The breakthrough came from assembling data from multiple Hubble Space Telescope observing programs. Over the years, Hubble has pointed at many regions in and around Andromeda for various science projects. Sometimes those observations happen to catch background quasars in the field of view. By searching through archived data, researchers assembled a sample of 43 confirmed quasars located at just the right positions to probe Andromeda's halo structure. Each quasar serves as a cosmic flashlight. Its light leaves the quasar billions of years ago, when the universe was younger and very different. That light races across space at 300,000 kilometers per second, covering unimaginable distances. Along the way, it passes through clouds of intergalactic gas, the halos of intervening galaxies, and eventually, Andromeda's extended atmosphere. Each gas cloud it encounters leaves a mark. The mark appears as an absorption line in the quasar's spectrum. Remember that spectra work by splitting light into its component wavelengths, like a prism spreading sunlight into a rainbow. A quasar's spectrum normally shows a smooth distribution of light across all wavelengths, but when light passes through gas, atoms absorb photons at specific wavelengths corresponding to their internal energy levels. These absorptions create dark lines in the spectrum, gaps where light is missing. Different elements create different patterns of absorption lines. Hydrogen produces one set of lines, oxygen another, carbon a third. By identifying which lines appear in a quasar's spectrum, scientists can determine what elements exist in the gas between the quasar and Earth. The strength of each line reveals how much of that element is present. The wavelength position tells you the velocity of the gas relative to Earth, because Doppler shifts move the lines toward the red or blue end of the spectrum. The Hubble Space Telescope's Cosmic Origins spectrograph specializes in ultraviolet spectroscopy, perfect for detecting absorption from ionized gas. Many of the most useful spectral features appear in the ultraviolet, wavelengths blocked by Earth's atmosphere, but easily observed from Hubble's orbit. The instrument can detect absorption from incredibly small amounts of gas, making it sensitive enough to map even the thin outer regions of Andromeda's halo. By comparing spectra from all 43 quasars, researchers built a three-dimensional picture of the halo. Quasars appearing close to Andromeda's visible disk showed strong absorption from many elements, indicating light passed through dense inner halo regions. Quasars farther from the galaxy showed weaker absorption, sampling more distant parts of the halo. Quasars in different directions around the galaxy revealed how halo properties vary with angle and position. This technique, called absorption line spectroscopy, has revolutionized the study of gaseous structures in the universe. It works for individual galaxies like Andromeda, for galaxy clusters, and even for the diffuse gas-filling intergalactic space. Wherever light from a background source passes through foreground gas, absorption lines encode information about that gas's properties. The method requires patience and careful analysis, but yields results impossible to obtain any other way. The Project Omega team spent years analyzing their quasar spectra. Each spectrum required detailed modeling to separate absorption from Andromeda's halo, from absorption created by other sources along the line of sight. The Milky Way's own halo produces absorption lines that can confuse the analysis. Intergalactic gas clouds between us and Andromeda also leave their mark. Distinguishing these various contributions required sophisticated computer models and cross-checking between multiple quasars. The resulting map exceeded all expectations. Not only did it reveal the halo's enormous size, but it also showed structure nobody anticipated. The double shell architecture, the velocity patterns, the chemical abundance variations across different regions. Without those 43 quasars, none of this would have been discovered. But knowing the halo exists raised new questions about what it contains. Chapter 10. The heavy element contamination. The halo is polluted. Across 1 million light-years of space, elements forged in the hearts of dying stars drift in a thin, invisible cloud. Oxygen, carbon, silicon, iron, and dozens of other heavy elements contaminate what should be pure primordial hydrogen and helium. This contamination tells the story of 10 billion years of stellar evolution and violent death. In the beginning, the universe contained only the lightest elements. Big Bang nucleosynthesis created hydrogen, helium, and tiny amounts of lithium, but nothing heavier. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, formed inside stars that lived and died before our own star existed. These elements spread through space when stars exploded, seeding future generations of stars and planets with the raw materials for rocky worlds and complex chemistry. The spectral analysis of quasar light revealed shocking amounts of heavy elements throughout Andromeda's halo. Even in the outermost regions, 2 million light-years from the galactic center, oxygen and carbon appeared in detectable quantities. The concentration remained low by terrestrial standards, less than 1 part per billion in many places. But compared to pure primordial gas, which should contain essentially zero heavy elements, this level of contamination requires explanation. The contamination comes from supernovae, exploding stars powerful enough to eject material completely out of the galactic disk. When a massive star reaches the end of its life, its core collapses in a fraction of a second, then rebounds in an explosion, releasing as much energy as the star radiated throughout its entire previous existence. The blast wave races outward at 30,000 kilometers per second or more, fast enough to escape the galaxy's gravity if it travels perpendicular to the disk. The explosion ejects several stellar masses worth of material. Much of this material consists of newly synthesized elements created during the star's final moments. Silicon, sulfur, and other elements form through fusion reactions in the collapsing core. Even heavier elements like iron and nickel form during the explosion itself, created by the incredible temperatures and densities present in the shockwave. This freshly forged matter blasts into space, mixing with pre-existing gas and spreading heavy elements through the environment. In a typical galaxy, most supernova ejecta stays in the disk, confined by the weight of overlying gas. But some fraction shoots upward or downward, perpendicular to the disk plane, where less material exists to slow it down. This escaping gas carries heavy elements into the halo, gradually enriching the entire volume around the galaxy. Over billions of years and hundreds of millions of supernovae, the cumulative effect builds up significant contamination even at great distances. The pattern of contamination reveals which types of supernovae contributed most. Different supernova types produce different element ratios. Core collapse supernovae, which occur when massive stars die, generate lots of oxygen and silicon, but relatively less iron. Type Ia supernovae, which happen when white dwarf stars explode after gaining too much mass, produce copious iron but less oxygen. By measuring the relative abundances of different elements in various regions of the halo, scientists can determine the contribution from each supernova type. The inner halo shows clear signatures of recent core collapse supernovae. The oxygen to iron ratio indicates massive stars exploded in the disk within the past few 100 million years, ejecting their debris into the surrounding space. The outer halo shows a slightly different pattern, with more iron relative to oxygen. This suggests the outer regions were contaminated longer ago, when earlier generations of stars evolved and contributed to the enrichment process. This chemical contamination has profound implications for star formation. When gas from the halo eventually falls back into the galactic disk, it carries these heavy elements with it. The next generation of stars that forms will have higher metallicity, containing more elements beyond hydrogen and helium. Higher metallicity affects everything about how stars behave, from their internal structure to their lifespan to the types of planets that can form around them. The contamination also connects to the concept of the galactic fountain. Gas heated by supernovae in the disk rises into the halo, cools over millions of years, then falls back to form new stars. This cycle continuously enriches the galaxy, slowly increasing the heavy element content generation by generation. Andromeda's halo captures this process in action, with hot, rising material in the inner shell and cooler, falling material in certain regions of the outer shell. Measuring heavy element abundances required analyzing extremely faint absorption features in the quasar spectra. Many elements produce absorption lines only in the ultraviolet, where Earth's atmosphere blocks all light. This made Hubble's cosmic origins spectrograph essential for the work. The instrument's sensitivity allowed detection of absorption from elements present at concentrations of only a few atoms per cubic meter, remarkable considering that typical air on Earth contains about 2 × 10 to the 19th power atoms per cubic centimeter. The most surprising discovery came from comparing the total mass of heavy elements in the halo to the total amount created by Andromeda's stars throughout cosmic history. Theoretical models predict how many supernovae should have occurred based on the galaxy's star formation history. Each supernova creates a predictable amount of heavy elements. Multiplying the two numbers gives an estimate of the total metal production. The calculation reveals that nearly half of all heavy elements ever created by Andromeda's stars now reside in the halo, expelled far beyond the stellar disk. This represents an enormous amount of material, equivalent to billions of stellar masses worth of processed matter. Andromeda has not kept most of the elements its stars created. Instead, it has blown them into a vast cloud surrounding the galaxy. This raises questions about efficiency. Why do galaxies expel so much enriched material? Does this limit how many stars they can form? What happens to gas that escapes the halo entirely, lost to intergalactic space? These questions remain active areas of research, but understanding the contamination provides only part of the story. The total mass involves much more than just heavy elements. Chapter 11: The Mass Calculation Shock. 500 billion times the mass of our own star hangs suspended in Andromeda's halo. This represents at least half as much mass as all the stars in the visible disk combined, possibly even more. For decades, astronomers focused on counting stars to estimate galactic mass, ignoring or underestimating the enormous reservoir of gas surrounding every major galaxy. The new measurements forced a complete recalculation of how massive Andromeda truly is. Measuring the mass of an invisible gas cloud presents serious challenges. Unlike stars, which shine and can be counted, diffuse gas reveals itself only indirectly through absorption lines in background quasar spectra. The strength of these lines indicates how much gas lies along each line of sight, but converting that information into total mass requires careful modeling and several assumptions about the gas distribution. The key measurement involves the column density, which describes how many atoms of a particular element exist along a line from the observer to the background light source. Higher column density produces stronger absorption. By measuring absorption strength for multiple elements and comparing to theoretical predictions, scientists can estimate the total amount of gas present. This works because the ratios between different elements remain roughly constant, set by stellar nucleosynthesis processes. The Project Omega team measured column densities toward all 43 background quasars. Each measurement sampled a different path through the halo, like drilling core samples through an invisible cloud. Some lines of sight passed through the dense inner regions, others through the diffuse outer halo. By combining measurements from many directions, the team built a model of how gas density varies with distance from the galactic center and position within the halo. The results showed exponentially declining density as distance increases, exactly as theoretical models predict. The inner halo, where supernovae directly influence the gas, maintains higher density than the outer regions. But even at the greatest distances, measurable amounts of gas persist. Integrating the density over the entire volume gives a total mass estimate that shocked the research community. The halo contains at least 500 billion stellar masses worth of gas. For comparison, our own star has a mass of 2 times 10 to the 30th power kilograms. Multiply that by 500 billion to get the halo's mass. The number defies comprehension. Written out fully, it requires 32 zeros after the 2. This represents only a lower limit. The measurements can only detect ionized gas that produces observable absorption lines. Neutral hydrogen, which does not show up in the ultraviolet spectra used for the study, might contribute additional mass. Cold molecular gas, if it exists in the halo at all, would also escape detection by this technique. The true total mass could exceed the measured value by 20 or 30%. Adding halo mass to stellar mass produces a more complete picture of Andromeda's total baryonic mass. Baryonic mass means ordinary matter, the protons, neutrons, and electrons that make up atoms. It excludes dark matter, which contributes even more mass, but remains invisible and undetectable except through gravitational effects. The combined baryonic mass of stars plus gas probably exceeds 2 trillion stellar masses, making Andromeda one of the most massive galaxies in the entire local group. The existence of this massive halo raises fundamental questions about galaxy formation and evolution. Where did all this gas come from? Some of it clearly represents material expelled from the disk by supernovae, enriched with heavy elements created in stars. But much of the halo likely consists of primordial gas that never condensed into stars, material left over from the galaxy's initial formation over 10 billion years ago. The halo also represents a future reservoir for star formation. Gas currently floating in the halo will eventually cool and fall back into the disk, providing raw material for new generations of stars. This recycling process can continue for billions of years, with each cycle extracting a bit more hydrogen from the halo and converting it into stars. Eventually, the reservoir will deplete, star formation will slow, and the galaxy will fade as its stellar population ages without replacement. The mass measurement also impacts our understanding of the upcoming collision with the Milky Way. When 2 galaxies merge, their total mass determines many aspects of the resulting system. More mass means stronger gravity. which affects how violently the galaxies interact and how long the merger process takes. The fact that Andromeda contains far more mass than previously estimated, with much of that mass distributed in an extended halo, changes predictions about what the collision will look like. Computer simulations of galaxy mergers typically assume most mass concentrates in the stellar disk, with relatively little material in the surrounding halo. The Andromeda measurements show this assumption is wrong. The halo contains comparable mass to the disk, distributed over a much larger volume. When the galaxies collide, their halos will interact first, compressing and heating the gas before the stellar components ever touch. This could trigger star formation in the halo itself, creating unusual stellar populations that form in low-density environments far from the galactic disk. The measurement techniques used for Andromeda's halo can be applied to other galaxies as well. Similar studies are underway for several nearby systems, attempting to map their halos using the same quasar absorption methods. Early results suggest that massive halos are common, not unique to Andromeda. This means previous estimates of galaxy masses throughout the universe may be systematically too low, potentially by factors of 2 or more. Revising these mass estimates affects cosmological models that depend on knowing how much baryonic matter exists in galaxies versus intergalactic space. The balance between these two reservoirs constrains theories about how structure formed in the universe and how galaxies grow over time. If a significant fraction of baryonic matter hides in invisible halos around galaxies, that changes the accounting and requires adjustments to the models. But knowing Andromeda's mass and size raises the next logical question. How fast is this massive galaxy moving? Chapter 12. The approaching speed measurement. 110 kilometers per second. That represents Andromeda's velocity toward the Milky Way, a speed that sounds modest when compared to the vast distances involved. Yet this motion, sustained over billions of years, will eventually close the gap between the galaxies and bring them crashing together. The measurement of this speed stands as one of astronomy's great technical achievements, confirmed and refined over decades of observations. The first hint came over a century ago. In 1912, astronomer Vesto Slipher at Lowell Observatory measured the spectrum of Andromeda and made a startling discovery. The absorption lines created by elements in the galaxy's stars appeared shifted toward the blue end of the spectrum. Every other galaxy Slipher studied showed redshift, their light stretched toward longer wavelengths by the expansion of the universe. Andromeda alone showed blue shift. Blue shift indicates motion toward the observer, just as an ambulance siren sounds higher pitched when approaching. The amount of shift reveals the velocity. Slipher calculated that Andromeda approaches at roughly 300 kilometers per second. At the time, nobody knew what Andromeda actually was. Many astronomers believed it might be a nebula within our own galaxy rather than a separate galaxy altogether. The high velocity seemed bizarre for an object supposedly bound to the Milky Way. Later observations refined the velocity measurement downward to about 110 kilometers per second. The correction came from better understanding of how Earth and the entire solar system move through space. We orbit the galactic center at 220 kilometers per second, and the solar system also has a peculiar velocity, motion relative to the average of nearby stars. Accounting for these motions accurately requires subtracting them from the observed Doppler shift to find Andromeda's true velocity relative to the Milky Way. 110 kilometers per second translates to about 250,000 miles per hour. Imagine traveling at that speed. You could circle Earth's equator in less than 2 hours. You could reach the moon in under 90 minutes. Yet, at this velocity, closing the 2.5 million light-year gap to the Milky Way takes billions of years. Space is so vast that even enormous speeds appear glacial when measured against cosmic distances. This velocity measurement reveals only part of Andromeda's motion. It gives the radial velocity, how fast the galaxy moves toward or away from us along the line of sight. It says nothing about sideways motion, called proper motion or tangential velocity. If Andromeda has significant tangential velocity, It might slide past the Milky Way rather than colliding head-on. Determining whether a collision will occur requires measuring the full three-dimensional velocity vector. Measuring proper motion for an object 2.5 million light-years away challenges the limits of observational astronomy. The angular motion is incredibly small, measured in millionths of an arcsecond per year. For comparison, 1 arcsecond equals the angle subtended by a dime viewed from 2 miles away. Now divide that already tiny angle by another million. Detecting motion that small demands the most precise instruments available and observations spanning many years, the Hubble Space Telescope finally provided the needed measurements. Starting in 2002, astronomers used Hubble to photograph stars in Andromeda with extreme precision. They repeated the observations in 2010, providing an 8-year baseline. By measuring how the positions of thousands of stars shifted relative to distant background galaxies, the team determined Andromeda's proper motion with unprecedented accuracy. The results showed sideways motion of less than 0.1 milliarcseconds per year, corresponding to a tangential velocity of less than 200 kilometers per second relative to the Sunday. Taking into account the solar system's own motion around the Milky Way, this translates to tangential velocity much smaller than the radial velocity. Andromeda is heading almost straight toward us, not sliding sideways. This measurement took extraordinary care. Each Hubble observation captured hundreds of stars within small regions of Andromeda. The stars appear so close together in Hubble's images that sophisticated software was needed to measure each one's position accurately. Background galaxies, much more distant and therefore essentially stationary over the 8-year interval, served as reference points. By measuring how Andromeda's stars moved relative to these fixed background galaxies, researchers extracted the tiny proper motion signal. The measurement uncertainty remained large enough that some sideways motion could exist without detection. The galaxy might have tangential velocity up to 100 kilometers per second, either northward or southward on the sky. This uncertainty propagates into predictions about collision, timing, and geometry. Even small differences in tangential velocity change, whether the galaxies hit head-on or strike at an angle. The approaching velocity also tells us something about the history of these galaxies. In an expanding universe, most galaxies move away from each other as space itself expands. The fact that Andromeda approaches means the gravitational attraction between the galaxies overcomes cosmic expansion. The two galaxies are not flying toward each other through empty space. Instead, they sit embedded in a gravitationally bound structure called the local group, a collection of dozens of galaxies all held together by their mutual gravity. Within the local group, the Milky Way and Andromeda dominate the mass budget. Their combined gravity shapes the motion of all smaller galaxies in the group. Computer simulations show that objects in such configurations eventually merge, pulled together by their mutual attraction. The current inward velocity represents the beginning of this merging process. The galaxies have probably been approaching for billions of years, slowly picking up speed as their separation decreases and gravitational force strengthens. The velocity also affects predictions about collision violence. A faster impact would create more dramatic effects, with stronger shock waves heating gas and triggering more intense bursts of star formation. The measured 110 kilometers per second falls in the middle of the range of possible values, neither extremely slow nor extremely fast. This suggests the collision, if it happens, will be energetic, but not catastrophic, producing a merger rather than complete disruption. But recent measurements have called the entire collision scenario into question. Chapter 13. The Collision Timeline Uncertainty. 4 billion years. 8 billion years. Maybe never. The timeline for Andromeda's collision with the Milky Way has grown increasingly uncertain as measurements improve and models become more sophisticated. What seemed like a certainty just a decade ago now appears as a probability, with outcomes ranging from violent merger to near miss that leaves both galaxies intact. The early predictions assumed a straightforward two-body problem. Andromeda and the Milky Way approach each other under mutual gravitational attraction. Calculate the current velocities and distances, apply Newton's laws, and the collision time falls out of the equations. Those simple calculations suggested 4 billion years until first contact, with full merger complete around 7 billion years from now. Many popularizations of astronomy still quote these numbers. The problem is that space does not contain only two galaxies. The local group includes over 80 known members, ranging from dwarf galaxies containing just a few million stars to massive systems like Andromeda and the Milky Way. Each of these galaxies has its own mass and its own motion. They all pull gravitationally on each other in a complex dance of mutual attraction and orbital motion. Ignoring these additional players introduces errors into the collision prediction. The Triangulum galaxy, also called M33, ranks as the third most massive local group member. It contains perhaps 40 billion stars, much smaller than Andromeda or the Milky Way, but still substantial. Triangulum orbits somewhere between the two larger galaxies, possibly bound to Andromeda, but the details remain uncertain. Computer simulations, including Triangulum, show it affects the collision timeline, potentially accelerating the merger by increasing the total mass pulling the galaxies together. The Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, also matters. Though smaller than Triangulum, containing only about 30 billion stars, its proximity means it exerts significant gravitational influence on the Milky Way's motion. The Large Magellanic Cloud is currently falling toward the Milky Way and will likely merge with our galaxy within the next 2 billion years. This merger will change the Milky Way's mass and velocity, affecting how it interacts with Andromeda afterward. Recent simulations by Sawala and colleagues incorporated data from the Gaia spacecraft and Hubble Space Telescope to measure positions and velocities of local group galaxies with unprecedented precision. They ran thousands of simulations, each time varying the input parameters slightly within their measurement uncertainties. This statistical approach reveals not just one possible future, but a range of outcomes with associated probabilities. The results shocked many astronomers. When including only the Milky Way and Andromeda, collision probability dropped to slightly less than 50%. Adding Triangulum increased the chances to about 67%. But when they included the Large Magellanic Cloud and its gravitational effects, the probability fell back to essentially a coin flip. Half the simulations ended in merger, half showed the galaxies swinging past each other without colliding. Even more surprising, the simulations that did produce mergers showed much longer timescales than previous predictions. Instead of 4 billion years until first contact, many simulations suggested 8 billion years or more. The additional masses in the system and their gravitational effects slow the approach, giving the galaxies more time before their eventual encounter. This uncertainty reflects fundamental challenges in predicting gravitational dynamics over billion-year timescales. The orbits are chaotic in the mathematical sense, meaning tiny differences in initial conditions produce dramatically different outcomes. A velocity change of just a few kilometers per second, well within current measurement uncertainties, can determine whether galaxies collide or miss. Small errors in measuring galaxy masses have similar effects. The situation resembles trying to predict whether two hurricanes will merge based on measurements of their current positions and wind speeds. Even with excellent data, the chaotic nature of the system limits prediction accuracy. Small perturbations grow exponentially over time, eventually dominating the outcome. For galaxies separated by millions of years of evolution, the compounding uncertainties become enormous. The collision uncertainty also stems from our imperfect knowledge of dark matter. Visible stars and gas account for only about 15% of a galaxy's total mass. The remaining 85% consists of dark matter, invisible particles that interact only through gravity. We can infer dark matter's presence from how it affects stellar motions, but mapping its exact distribution remains difficult. Since dark matter provides most of the gravitational force driving the collision, uncertainties in its distribution translate directly into uncertainties about collision probability and timing. The realization that collision is not inevitable changes how astronomers think about the future. Previous popular accounts confidently described the merger as our galaxy's destiny, inevitable as sunrise. Now, scientists speak more carefully about probabilities and ranges of outcomes. The merger might happen, transforming our local corner of the universe into something unrecognizable, or the galaxies might swing past each other, gravitationally disturbed but remaining separate entities for billions of years more. This uncertainty should not be seen as failure. Rather, it reflects honest acknowledgement of measurement limitations and modeling challenges. Science progresses not just by learning new facts, but by understanding the boundaries of our knowledge more clearly. We now know that predicting galaxy collisions over billion-year timescales requires better data and more sophisticated models than currently available. Future observations might reduce the uncertainty. The Gaia spacecraft continues measuring stellar positions and motions throughout our galaxy and beyond. Extended observations will improve velocity measurements for Andromeda, shrinking error bars and constraining possible outcomes. Better dark matter mapping, using gravitational lensing and stellar dynamics, will refine mass estimates. Each improvement in the data narrows the range of possible futures. But even with perfect data, some irreducible uncertainty will remain. The system is genuinely chaotic, with sensitivity to initial conditions that cannot be measured with infinite precision. We may never be able to say with certainty whether the collision will occur until it actually happens, or does not happen, billions of years in the future. Regardless of the exact timeline, one thing remains clear. The approach continues. Chapter 14. The probability, calculation, shift, 50%. A coin flip. The odds that Andromeda and the Milky Way will actually collide have dropped from near certainty to an even chance. This dramatic shift in probability stems from including factors that previous calculations ignored, particularly the gravitational influence of smaller galaxies that seemed too minor to matter. They matter enormously. The original collision predictions treated the local group as if only 2 galaxies existed. This approximation worked reasonably well for initial estimates, because Andromeda and the Milky Way dominate the local mass budget so thoroughly. Together they account for roughly 90% of all stellar mass within several million light-years. Compared to these behemoths, galaxies like Triangulum and the Large Magellanic Cloud seemed negligible. Gravitational dynamics does not work that way. Even small masses can have outsized effects over long timescales, especially when those masses sit at crucial positions. The Large Magellanic Cloud, though containing only about 10% of the Milky Way's stellar mass, orbits close enough that its gravitational tug affects our galaxy's motion significantly. As the Large Magellanic Cloud falls toward the Milky Way over the next billion years, it will alter our galaxy's velocity and trajectory. Think of it like a game of pool. The white cue ball might be heading straight for a colored ball, but if a third ball rolls past just before collision, its gravitational influence, however slight, can deflect the cue ball's path enough to cause a miss. The local group resembles a cosmic pool table with dozens of balls in play, each exerting tiny forces that accumulate over billions of years into substantial changes in trajectory. The Sawala team's simulations ran the same basic scenario thousands of times, each run varying the input parameters within measurement uncertainties. In some runs, they placed Triangulum slightly closer to Andromeda. In others, they adjusted the Large Magellanic Cloud's velocity by a few kilometers per second. They varied Andromeda's tangential motion across its allowed range. They modified mass estimates up and down within error bars. Each small change produced a different evolution of the system. When they included only the Milky Way and Andromeda, ignoring all other galaxies, 46% of simulations ended in collision within 10 billion years. The rest showed the galaxies swinging past each other, disturbed by their close encounter but avoiding merger. This already represented lower odds than traditional predictions, which generally assumed collision was inevitable. Adding Triangulum to the simulations increased the collision probability to 67%. Triangulum's mass, positioned between the 2 larger galaxies, enhances their mutual attraction slightly, and helps pull them together. The effect is small, but statistically significant across thousands of simulation runs. With triangulum included, 2/3 of possible futures end in merger. The surprise came when including the Large Magellanic Cloud. Despite being smaller than triangulum and farther from Andromeda, the Large Magellanic Cloud's gravitational effects reduced collision probability back down to 50%. The reason involves timing. The Large Magellanic Cloud will merge with the Milky Way relatively soon, probably within 2 billion years. This merger will change the Milky Way's velocity vector, potentially deflecting it enough to miss Andromeda entirely. The effect depends sensitively on exactly when and how the Large Magellanic Cloud merger occurs. If it merges from one direction, the resulting velocity change nudges the Milky Way toward Andromeda. If it merges from a different angle, it pushes our galaxy away. With current uncertainties about the Large Magellanic Cloud's orbit, both scenarios remain equally plausible. The averaging across many possibilities produces the 50% result. This probability shift has philosophical implications for how we think about cosmic fate. Humans generally prefer certainty. We find comfort in knowing what will happen, even if that future event lies billions of years away. The idea that our galaxy's destiny reduces to a coin flip feels unsatisfying. We want to know whether the collision will occur, not just that it might or might not. Science cannot always provide the certainty we desire. The universe is probabilistic at quantum scales, and apparently remains so at galactic scales as well, though for different reasons. Quantum uncertainty arises from fundamental limits on measurement. Galactic collision uncertainty comes from chaotic dynamics and measurement precision, problems that could in principle be solved with better data. But until that data arrives, we must accept probabilistic predictions. The 50% number should not be taken too literally. It represents the fraction of simulated futures that ended in collision given current measurement uncertainties. As measurements improve, the probability will shift. Better velocity data for Andromeda might increase the chance to 70% or decrease it to 30%. We will not know which until those measurements arrive. Some astronomers question whether the question even makes sense in its current form. Asking whether the galaxies will collide implies a binary outcome, collision or no collision. Real galaxy interactions exist on a spectrum. A glancing blow that strips gas and triggers some star formation, but leaves both disks mostly intact, might not qualify as a full collision, yet it hardly counts as missing each other either. The simulations show a range of encounter distances, from direct hits to widely separated flybys, with all possibilities in between. Defining collision probability requires choosing some threshold distance and counting how many simulations bring the galaxies closer than that limit. Change the threshold and the probability changes too. This arbitrariness makes the 50% number somewhat artificial, dependent on definitions rather than reflecting physical reality directly. Still, the calculation serves a useful purpose. It quantifies our uncertainty. 10 years ago, astronomers confidently predicted collision. Today, honest assessment of the data and models admits we simply do not know. That represents progress in understanding what we do not understand, a crucial but often overlooked aspect of scientific advancement. The probability also reminds us that cosmic evolution proceeds through chance as much as determinism. Initial conditions set billions of years ago, quantum fluctuations in the early universe, determine whether galaxies form here or there, whether they acquire this much mass or that much. Those random variations propagate forward, producing the specific configuration of the local group we observe. With slightly different initial conditions, Andromeda might be farther away, moving slower, or angled differently. Our future depends on ancient chance. But probability alone does not capture the full complexity. Even knowing whether collision will occur, we need to understand the encounter geometry. Chapter 15. The lateral motion problem. The measurement seems impossible. Detect motion across the sky for an object 2.5 million light-years away. when that motion amounts to less than 1/10 millionth of a degree per year. This represents the angular equivalent of watching a human hair grow from the distance of the moon. Yet astronomers needed exactly this measurement to predict whether Andromeda and the Milky Way will collide or miss. The problem is that radial velocity alone tells an incomplete story. Knowing Andromeda approaches at 110 kilometers per second reveals only the component of motion along our line of sight. The galaxy might also move sideways, northward or southward across the sky, as seen from Earth. This tangential or lateral motion determines collision geometry. If the sideways velocity is large enough, Andromeda will slide past rather than hitting head-on. Astronomers call this sideways motion proper motion, measured in angular units per time, typically arcseconds per year or milliarcseconds per year. For nearby stars, proper motion can be substantial. Barnard's star, one of our closest neighbors at 6 light-years, moves 0.5 arcseconds per year across the sky, easily measurable with modest telescopes. More distant stars have proportionally smaller proper motions. A star 100 times farther shows 100th the angular motion for the same physical velocity. Andromeda lies 400,000 times farther than Barnard's star. If it moved at similar velocity to that nearby star, its proper motion would be 1,000,000 times smaller, around 0.0005 milliarcseconds per year. Actually measuring such tiny motions requires technology that did not exist until the 21st century. The Hubble Space Telescope provided the needed capability. Hubble's sharp imaging, above the blurring effects of Earth's atmosphere, can measure stellar positions to within a few milliarcseconds. By photographing the same field twice with many years between observations, astronomers can detect tiny shifts in star positions. The challenge is distinguishing real motion from measurement errors and systematic effects that also produce apparent shifts. The team led by Roland van der Marel at the Space Telescope Science Institute designed a careful observing program. They selected several fields in Andromeda rich with bright stars, regions where precise position measurements would be easiest. They imaged these fields in 2002 and again in 2010, providing an 8-year baseline. The longer the time between observations, the larger the motion to be measured and the easier the detection becomes. But they could not simply measure how star positions changed between the two epochs. Hubble itself moves, orbiting Earth every 96 minutes. Earth orbits, the change in that motion would produce apparent stellar shifts, having nothing to do with Andromeda's actual motion through space. The solution involved using background galaxies as reference points. These distant galaxies, lying billions of light-years beyond Andromeda, move negligibly across the sky over human timescales. They serve as a fixed coordinate system against which to measure Andromeda's motion. By tracking how Andromeda's stars shifted relative to these background galaxies, the team isolated the proper motion signal. The analysis required extraordinary care. The team measured positions for thousands of stars in each field, averaging together many measurements to beat down random errors. They checked for systematic effects that might bias the results. Different parts of Hubble's camera respond slightly differently to light, potentially introducing false shifts. Temperature changes in the telescope structure can alter the optical path between observations. The team corrected for these effects using sophisticated calibration procedures. The final result showed proper motion of less than 0.05 milliarcseconds per year, at the very limit of what Hubble can measure. This corresponds to tangential velocity of less than 100 kilometers per second, significantly smaller than the radial velocity component. The measurement uncertainty remains large, about plus or minus 50 kilometers per second. Andromeda could be moving northward or southward by up to 50 kilometers per second without violating the observations. This remaining uncertainty has enormous consequences. Even 50 kilometers per second, sustained over 4 billion years, translates to 200,000 light-years of lateral displacement. That exceeds the diameter of either galaxy's stellar disk. A sideways velocity in that range could easily shift the impact point from head-on to glancing blow or even complete miss. The proper motion measurement also depends on knowing Andromeda's distance precisely. If the galaxy sits slightly farther than 2.5 million light-years, the same angular motion corresponds to higher physical velocity. If it sits closer, physical velocity would be lower. Current distance uncertainties of a few percent translate into velocity uncertainties of similar magnitude, adding to the challenge of predicting collision geometry. Future observations will improve these measurements. The Gaia spacecraft, launched in 2013 to map positions and motions of stars throughout our galaxy, has also measured positions of some bright objects in Andromeda. As Gaia continues operating, building up longer time baselines, its measurements will provide independent checks on proper motion. The James Webb Space Telescope, with sensitivity surpassing Hubble's, might also contribute measurements for fainter stars in Andromeda. The lateral motion problem highlights a general challenge in astronomy. We observe the universe from a single vantage point, seeing only one face of every object. Motions perpendicular to our line of sight, which dominate the dynamics of many systems, remain difficult or impossible to measure directly. We must infer them from indirect evidence or wait decades for tiny proper motions to accumulate into detectable signals. For Andromeda, the lateral motion uncertainty means we cannot definitively predict collision geometry. The galaxy might hit head-on, maximizing the violence and destruction, or it might strike at an angle, producing a less dramatic merger, or it might miss entirely, swinging past in a close encounter that disturbs both galaxies but leaves them separate. The answer lies hidden in a motion too small to see, but large enough to determine the fate of 1 trillion stars. Chapter 16. The glancing blow scenario. The galaxies might sideshow, instead of colliding head-on. This changes everything about how the merger unfolds. A glancing blow produces less violent disruption, longer interaction times, and stranger outcomes than a direct impact. Current measurements cannot rule out this scenario, leaving open the possibility of a cosmic fender bender rather than a head-on crash. Glancing blows happen commonly in galaxy collisions. Computer simulations show that unless two galaxies approach on nearly perfect collision courses, they will strike at some angle. The geometry depends on their relative velocities in 3 dimensions and the exact alignment of their orbital planes. Even small deviations from head-on geometry change the merger dynamics substantially. In a glancing encounter, the galaxies initially pass by each other rather than interpenetrating immediately. Their gravitational pull stretches each galaxy as they pass, drawing out long tidal tails of stars and gas streaming behind. These tidal tails can extend for hundreds of thousands of light-years, creating spectacular structures visible in telescope images. The Andromeda Galaxies, a famous colliding pair visible in Earth's southern sky, show this process beautifully. After the first passage, gravity bends each galaxy's trajectory, pulling them back toward each other. They swing around for a second encounter, this time approaching from different angles than initially. If they still miss making direct contact, they pass again, spiraling closer with each swing. The process can repeat multiple times over billions of years, with the galaxies dancing around each other in an ever-tightening embrace. This extended merger produces less violent effects than a head-on collision. When galaxies hit straight on, their gas clouds collide at high relative speeds, creating powerful shock waves that heat gas to millions of degrees. The shock compression triggers intense bursts of star formation as dense regions collapse rapidly. A head-on collision can form millions of new stars in just a few tens of millions of years, lighting up the merger region with brilliant blue light from massive young stars. Glancing blows spread these effects across longer timescales. The first passage disturbs gas clouds, but may not compress them enough to trigger major star formation. Subsequent passages add more compression, gradually ramping up star formation over hundreds of millions of years, rather than all at once. The result is less spectacular visually, but may ultimately produce similar total amounts of new stars, just spread across a longer timeline. The Andromeda Milky Way encounter could follow this glancing blow pattern, If measurements show significant tangential velocity, current data cannot rule it out. If Andromeda moves sideways at 50 kilometers per second or more, the first encounter will likely be a near miss rather than direct collision. The galaxies would distort each other gravitationally, creating tidal features and possibly triggering some star formation, but remain distinct entities after the passage. The orbital dynamics of a glancing blow depend on total system mass. More mass means stronger gravitational binding, making it harder for galaxies to escape after the first passage. Less mass allows galaxies to swing wider, potentially leading to multiple distant encounters before finally merging. For Andromeda and the Milky Way, the combined mass, including dark matter, is high enough that even a glancing first pass almost certainly leads to eventual merger. The question is not whether they will eventually combine, but how many passages the process requires. During each passage, energy dissipates through gravitational interactions. Individual star orbits within each galaxy change, converting some of the galaxy's orbital energy into random stellar motions. Gas clouds collide, heating up and radiating away energy as light. Each energy loss brings the galaxies closer together on their next approach. After several passages spanning billions of years, the separation shrinks until the galaxies finally merge completely. The glancing blow scenario affects predictions about our solar system's fate. In a head-on collision, the Sun might experience one violent encounter with stars from Andromeda, getting either ejected from the galaxy or pushed to a different orbital radius. In a glancing collision with multiple passages, the Sun experiences several less dramatic encounters, each changing its orbit slightly. The cumulative effect might be similar, but spread across a longer time period with less chance of immediate dramatic changes. Tidal tails produced by glancing encounters also distribute material far from the merger site. Some stars and gas clouds get flung to enormous distances, hundreds of thousands or even millions of light-years from the galaxies. These ejected objects form the diffuse stellar halo of the final merged galaxy. Globular clusters, ancient compact star systems that orbit in galaxy halos, may form partly from material stripped during glancing encounters. The exact encounter geometry remains unknown until better, proper motion measurements arrive. Each new observation slightly constrains the possibilities. The James Webb Space Telescope and continued Hubble observations will gradually shrink the error bars on tangential velocity. In another decade, we may know definitively whether to expect head-on collision or glancing blow. Interestingly, the glancing blow scenario might be more favorable for life in both galaxies. A head-on collision delivers a sudden burst of radiation from rapidly forming massive stars and subsequent supernovae. This radiation could sterilize planets across large regions of both galaxies. A slower, glancing merger spreads these effects across space and time, giving life on any affected worlds more opportunity to adapt or for planets to move to safer orbits through dynamical evolution. But regardless of encounter geometry, one fact remains certain: the halos are already interacting. Chapter 17. The already merging halos. The merger has begun, not billions of years in the future, but right now. The diffuse outer atmospheres of both galaxies overlap in the space between them, creating a boundary zone where gas from Andromeda and gas from the Milky Way already mix. This early interaction stage will continue for billions of years before the stellar components ever touch, representing the longest phase of the merger process. The halo interaction occurs because both galaxies possess enormous gaseous envelopes extending far beyond their visible disks. Andromeda's halo reaches 1.3 million light-years toward us, more than halfway across the 2.5 million light-year gap. The Milky Way, being similar in size and type to Andromeda, likely has a comparable halo extending in the opposite direction. Simple geometry shows these halos must overlap. Scientists mapped the Milky Way's halo less completely than Andromeda's because we view it from inside. Attempting to study the Milky Way's halo resembles trying to understand a forest's structure while standing among the trees. You see individual trees clearly, but perceiving the overall forest shape and extent proves difficult. We can measure gas absorption toward distant quasars that happen to lie in directions away from Andromeda, sampling our own halo in those directions. Those measurements reveal the Milky Way's halo extends at least 600,000 light-years, possibly much farther. If symmetry holds and our halo matches Andromeda's, it should reach outward at least 1 million light-years. Adding 1.3 million from Andromeda and 1 million from the Milky Way exceeds the 2.5 million light-year separation. The halos must be touching. The interaction zone should display distinct characteristics. As gas clouds from the two galaxies approach each other, they compress against each other like colliding weather fronts on Earth. The compression heats the gas, raising temperatures above what would exist in either halo alone. The pressure also slows the gas motion, creating a region where velocities differ from simple predictions based on each galaxy's individual motion. Finding direct evidence for this interaction zone proves challenging. The gas involved is already extremely diffuse, and the interaction region represents an even thinner boundary layer. Detecting it requires finding background quasars positioned perfectly to probe the space between the galaxies. Such quasars are rare because the zone occupies a relatively small area of sky, and most quasars lie either much closer or much farther away. Nevertheless, hints exist in the data. Some quasar spectra show gas absorption with velocities intermediate between what would be expected for pure Andromeda halo gas and pure Milky Way halo gas. This could indicate mixed regions, where gas from both galaxies coexists. The chemical composition of some absorbers also shows puzzling features, potentially explained by mixing of gas enriched differently in the two galaxies. The merging halos have important consequences for future star formation. Gas from Andromeda's halo, slowly diffusing across the boundary, will eventually rain down onto the Milky Way's disk. This provides fresh material for forming new stars, supplementing our galaxy's internal gas supply. Similarly, gas from our halo crosses into Andromeda's gravitational domain, fertilizing future star formation there. This cross-contamination means stars forming in either galaxy over the next few billion years may incorporate material originally expelled from the other galaxy. The chemical fingerprints in those future stars will record contributions from stellar populations in both galaxies, creating a hybrid signature. By the time the stellar disks finally merge, gas will have been mixing for billions of years already. The interaction zone also affects the local intergalactic medium. The volume of space within the local group contains gas not associated with any specific galaxy, material left over from early cosmic times or expelled by galaxies and never recaptured. The merging halos stir this intergalactic gas, creating currents and pressure variations. Some intergalactic gas might get swept up and incorporated into one halo or the other, growing the galaxies slightly even before they fully merge. Computer simulations of galaxy mergers generally ignore or oversimplify halo dynamics. Most simulations focus on the stellar and dark matter components, which dominate the gravitational dynamics. Gas receives less attention, partly because modeling gas physics correctly requires enormous computational resources. But the Andromeda-Milky Way halo interaction shows that gas dynamics in mergers begins far earlier than stellar dynamics, playing out over longer timescales. This early halo merger phase has no dramatic visual signatures, unlike the later collision of stellar disks, which produces spectacular tidal tails and intense starbursts visible across millions of light-years. The halo merger remains essentially invisible. Only through absorption line spectroscopy, studying how background quasar light changes, can we detect this subtle process. Yet this invisible interaction may prove more important than the visible collision. The halo contains as much mass as the stellar disk. How that mass moves, mixes, and eventually accretes onto the galaxies determines the star formation history over billions of years. The spectacular fireworks of stellar disk collision last mere hundreds of millions of years. The slow, steady influence of merging halos persists across the full multi-billion-year merger timeline. We stand at the beginning, watching the earliest stages of a process that will continue longer than Earth has existed. The halos touch, press together, begin mixing, Stars remain separated, galaxies still distinct. But the merger has begun, invisible yet inexorable, driven by the weak but patient force of gravity acting across vast gulfs of space. The interaction will only intensify as the galaxies draw closer over the next few billion years. Imagine looking up on a clear autumn night and seeing something impossible. A glowing arc stretches across 1/3 of the entire sky, wider than your outstretched hand at arm's length, dominating everything. This ethereal structure dwarfs every constellation, outshines the Milky Way's band, and makes the moon look tiny by comparison. You are seeing Andromeda's halo as if it glowed bright enough for human eyes to detect, 3 times the width of the Big Dipper. That measurement conveys the angular scale, but the visual impact would be staggering. The Big Dipper itself spans roughly 25 degrees across the sky. Triple that, and you get 75 degrees, more than 3/4 of a right angle. An observer standing under this apparition would need to turn their head significantly just to see from one edge to the other. The halo would not shine uniformly. The inner regions, closer to Andromeda's visible disk, would glow brighter from denser concentrations of ionized gas. Moving outward, the brightness would fade gradually, creating a diffuse gradient from bright core to barely perceptible edge. The structure would appear roughly spherical but slightly flattened, reflecting the disk structure of the galaxy generating it. Color would be subtle but present. Ionized oxygen emits blue-green light at specific wavelengths. Hydrogen contributes red emission. The combination would produce a pale, ghostly glow, perhaps resembling the aurora borealis, but spread across a much larger area. The overall luminosity would likely be low, bright enough to see clearly from dark locations, but washing out in areas with light pollution. If this halo were visible, it would become the defining feature of Earth's night sky. Ancient cultures would have built mythologies around it. Navigation would reference it. Seasonal changes in its position and visibility would mark the passage of time. The structure would be so prominent that forgetting about its existence would be impossible. Every human would grow up knowing that this enormous cosmic neighbor hangs in the darkness above. The visibility problem stems from surface brightness. Total luminosity measures how much energy an object radiates. Surface brightness describes how that energy spreads across the object's apparent area. An object can have high total luminosity, but low surface brightness if the light spreads thinly over a large area. Human eyes need concentrated light to trigger detection. Spread the same amount of light across 10 times the area, and it becomes effectively invisible. Andromeda's halo possesses substantial total luminosity from ionized gas emission, but this light distributes across millions of square arc-minutes of sky. The result is surface brightness far below human visual threshold, comparable to, or dimmer, than the darkest portions of the night sky itself. Only specialized instruments using long exposure times and narrowband filters can detect it at all. Scientists have created false color images, showing what the halo might look like if our eyes could integrate light over hours like a camera. These images reveal magnificent structure, shells within shells, variations in brightness tracing the dynamic inner regions versus smoother outer envelope. But these remain artistic representations of data, not visual experiences anyone will actually see. The visible disk of Andromeda, without the halo, already spans an impressive 6 times the moon's width. This remains difficult to appreciate visually because only the bright central core shows up easily to naked eyes. Under exceptional dark sky conditions, keen-eyed observers can trace the extended disk structure, seeing hints of the spiral arms. But most people see only a fuzzy oval, missing the true scale. If Andromeda were brighter while maintaining its current size, it would rank among the most spectacular celestial objects. Instead of requiring dark skies and good eyesight, it would be obvious to anyone who looked up. Urban dwellers would notice it between buildings. Airline passengers would point it out to each other through windows. It would appear in countless photographs as an unexpected photobomber, captured accidentally whenever cameras pointed toward that region of sky. The practical implications would be interesting. Astronomers would have discovered and studied Andromeda much earlier in history. Its detailed structure would have been mapped centuries ago. Understanding that galaxies exist as separate island universes might have come sooner. The whole history of astronomy and cosmology could have developed differently with such an obvious example of an external galaxy hanging in the sky. Conversely, light pollution would become an even more pressing issue. Already, artificial lighting from cities washes out most astronomical features for much of humanity. A bright Andromeda halo would be another casualty of light pollution, hidden from view by excessive urban illumination. Campaigns to preserve dark skies would cite this loss as a particularly poignant example of what technology takes from us. The halo's appearance would also change over time, though on scales too long for individual humans to notice. As the galaxies approach each other, Andromeda's apparent size grows infinitesimally larger each year. In 10 million years, assuming the galaxies continue approaching, the angular size would increase by measurable amounts. In 100 million years, the difference would be obvious when comparing historical images. In 1 billion years, assuming collision proceeds, the halo would grow noticeably larger, beginning to fill even more of the sky. During the eventual collision, if it occurs, the combined halo would temporarily increase in brightness. Compression zones, where gas from both galaxies collides, would heat up, emitting more strongly. For a period of perhaps 10 to 20 million years, during the most violent interaction phase, the merged halo might actually become marginally visible to naked eyes from perfect dark sky locations, appearing as an enormous, faint glow surrounding the clearly visible chaos of colliding galactic disks. But today, the halo remains invisible to unaided vision, detectable only through patient observation and sophisticated instruments. We know it is there, larger than anything else in our night sky, yet we cannot see it. This reminds us that the universe contains wonders hidden, not by distance, but by the limitations of our senses. What we perceive as reality represents only a tiny fraction of what actually exists. Andromeda's halo hangs above us every clear autumn night, vast and silent, invisible yet real. Its presence reshapes our understanding of galactic structure and coming collision dynamics. The fact that something so enormous can remain unseen offers a humbling perspective on how much we miss when we look at the sky. Yet even this massive halo formed through violent processes. The outer regions of Andromeda tell a violent story. The clumpy, irregular distribution of stars beyond 100,000 light-years from the galactic center records ancient catastrophes, smaller galaxies torn apart and consumed billions of years ago. Each irregularity traces a collision preserved in stellar orbits long after the carnage ended. Computer simulations reveal smooth, orderly, spiral galaxies cannot produce the observed structure naturally. When researchers model isolated galaxy evolution, starting with realistic initial conditions and letting physics run forward for billions of years, they create neat spirals with exponentially declining stellar density. The density drops smoothly from core to edge, with no major clumps or asymmetries in the outer disk. Andromeda's outer disk looks nothing like these smooth models. Instead, stellar density varies dramatically from place to place. Some regions contain concentrated clusters of stars. Other areas show almost no stars at all, creating apparent voids. The overall distribution appears chaotic rather than orderly, as if someone scattered stars randomly through the volume, rather than allowing them to settle into equilibrium configurations. The only way to create such structure involves external disruption. Something must have stirred the outer disk, injecting energy and angular momentum that prevents stars from settling into smooth distributions. The most effective stirring mechanism is galaxy collisions. When a smaller galaxy crashes into a larger one, the gravitational forces stretch and compress both systems. Stars from the small galaxy get scattered across a wide volume, creating exactly the kind of clumpy structures observed in Andromeda's outer regions. Evidence for past collisions appears throughout Andromeda. Stellar streams, long arcs of stars following similar orbits, trace the disrupted remnants of satellite galaxies. These streams can extend for hundreds of thousands of light-years, wrapping around the main galaxy like ribbons. Some streams show coherent motion patterns, with all stars moving together, proving they share a common origin. Others have dispersed over time, their stars scattered so thoroughly that only statistical analysis reveals the original stream structure. The giant stellar stream in Andromeda's outer regions represents one of the most dramatic examples. Discovered through wide-field imaging surveys, this stream contains millions of stars arrayed in a structure spanning 200,000 light-years. The stars share similar ages and chemical compositions, confirming they form together in a single progenitor galaxy. That galaxy, probably comparable in size to the large Magellanic Cloud orbiting the Milky Way, crashed into Andromeda several billion years ago. Reconstructing these ancient collisions requires careful analysis of stellar velocities and positions. Stars from destroyed satellites follow distinctive orbital patterns determined by the collision geometry and timing. By measuring velocities for individual stars in the streams and comparing to computer simulations, researchers can work backwards to determine when collisions occurred and what trajectories the satellite galaxies followed. The results show Andromeda has consumed at least a dozen smaller galaxies over its lifetime. Some collisions happened relatively recently, within the past billion years. Others occurred early in the galaxy's history, over 8 billion years ago. Each collision added mass to Andromeda, helping it grow from a smaller initial system into the massive galaxy we see today. The accumulation process continues even now, with several small satellite galaxies currently falling toward Andromeda and destined for eventual destruction. These past collisions also explain features in Andromeda's halo. The double shell structure, with distinct inner and outer regions, may partly result from merger events. Gas from infalling satellites gets shock-heated during collision, creating hot bubbles that expand into the halo. Multiple collisions over billions of years build up complex, layered structures as different bubbles interact and merge. The observed irregularities in temperature and density could trace individual merger events preserved in the halo gas. The collision history also affects star formation patterns. When satellites crash into the main disk, they compress gas clouds, triggering bursts of new star formation. These bursts create generations of stars with similar ages, appearing as distinct populations when analyzed spectroscopically. By studying the age distribution of stars throughout Andromeda, astronomers can identify these burst events and correlate them with collision timing inferred from stellar streams. Globular clusters provide additional clues. These ancient, compact star systems orbit in galaxy halos, and many probably formed during violent merger events. Andromeda possesses roughly 500 globular clusters, far more than the Milky Way's 150 or so. The excess likely results from Andromeda's more violent merger history, with each major collision creating new globular clusters from compressed gas clouds, while also transferring existing clusters from the satellite galaxy. The chemical composition of stars in the outer disk reveals surprising complexity. Some stars show enrichment patterns characteristic of Andromeda's main disk, indicating they formed within the galaxy. Others display different chemical signatures, suggesting formation in satellite galaxies before being accreted. Mapping these chemical variations traces which regions contain native stars versus immigrant stars from destroyed satellites. Understanding Andromeda's merger history helps predict what will happen when it collides with the Milky Way. Our upcoming merger represents just another in a long series of collisions Andromeda has experienced. The galaxy is battle-hardened, its structure shaped by repeated violent encounters. The Milky Way, by comparison, has had a relatively quiet history with fewer major mergers. How this difference affects merger dynamics remains an active research question. The satellite galaxies currently orbiting both Andromeda and the Milky Way will play roles in the collision. Some will get torn apart by tidal forces as the large galaxies interact. Others might get flung away, ejected from the system entirely. A few might survive the chaos, ending up as satellites of the final merged galaxy. Tracking the fates of these smaller systems requires including them in collision simulations, adding complexity but improving realism. Every galaxy grows through accretion. The largest systems form by consuming hundreds or thousands of smaller galaxies over cosmic time. Andromeda's clumpy outer disk provides a window into this process, showing us the aftermath of ancient meals long since digested. The same process will eventually consume both Andromeda and the Milky Way, merging them into a single remnant that will itself likely experience future collisions with other local group members. The story written in Andromeda's stars reminds us that galaxies are not static, eternal structures. They grow, change, collide, and merge. What we see represents only a snapshot in an ongoing evolution spanning the entire age of the universe. Looking at the clumpy outer disk is like examining fossils, finding preserved evidence of ancient events encoded in the distribution and motions of stars. These collisions shaped Andromeda into what it is today. The coming collision will shape it into something new, 4 billion years from now, or 8 billion, or perhaps never. If the collision occurs, everything changes. Two magnificent spiral galaxies, each containing hundreds of billions of stars, will transform into a single, enormous, elliptical galaxy. Astronomers have already named it Milky. Elliptical galaxies look nothing like spirals. They possess no spiral arms, no obvious internal structure, no defined disk. Instead, they appear as smooth, featureless blobs of stars with brightness declining gradually from center to edge. Stellar orbits in ellipticals appear random rather than organized. Some stars orbit clockwise, others counterclockwise. Some follow nearly circular paths. Others plunge through the galactic core on highly eccentric trajectories. The orderly rotation of spiral disks gives way to chaos. The transformation from spiral to elliptical occurs because galaxy collisions scramble stellar orbits. When two disk galaxies merge, gravitational forces during the interaction yank stars out of their circular orbits. Some get accelerated, others decelerated. Many acquire velocity components perpendicular to the original disk plane. After the merger completes, stars retain these jumbled orbits. The collective motion no longer defines a coherent disk, but instead creates a three-dimensional, ellipsoidal swarm. Computer simulations of Andromeda-Milky Way merger consistently produce elliptical galaxies as end products. The exact shape depends on collision geometry and relative velocities, but the outcome always lacks spiral structure. Some simulations produce nearly spherical ellipticals. Others create slightly flattened systems. The variation reflects different possible collision scenarios, but all result in the same basic morphological type. Milky will be massive, combining Andromeda's 1 trillion stars with the Milky Way's 300 billion produces 1.3 trillion stars, making it one of the largest galaxies in the local group. The mass, including dark matter, will exceed 3 trillion stellar masses, creating a gravitational potential well deep enough to bind a huge volume of space. Any remaining small galaxies in the local group will likely fall toward Milky and eventually merge with it, further increasing the mass. The size of Milky is harder to predict. Elliptical galaxies do not have well-defined edges like spiral disks. Instead, their stellar density fades gradually outward, approaching but never quite reaching zero. Astronomers define effective radius, the radius containing half the total light, as a size measure. For Milky, the effective radius will probably fall between 20,000 and 50,000 light-years, making it comparable in overall size to current Andromeda, but with stars distributed throughout the volume rather than concentrated in a disk. Star formation in Milky will eventually cease. Elliptical galaxies form few new stars because they lack the cold, dense gas needed for star formation. During the merger, gas clouds collide and heat up, either forming stars in intense bursts or heating beyond the temperature where they can collapse. After merger completes, most remaining gas will be hot, sitting in the halo rather than concentrated in a disk. Without cold gas supply, star formation drops to near zero. This means Milky stellar population will age without replacement. The massive blue stars present during the merger will explode as supernovae within a few tens of millions of years. Medium-mass stars like our own will evolve into red giants over billions of years. Eventually, only the smallest, longest-lived red dwarf stars will continue burning. The galaxy will fade, gradually dimming as its stellar population ages and dies. The central region of Milky will host a supermassive black hole formed by merging the black holes at the centers of Andromeda and the Milky Way. Andromeda's black hole contains roughly 140 million stellar masses. The Milky Way's black hole contains about 4 million stellar masses. When they merge, they will create a single black hole of 144 million stellar masses, releasing tremendous energy in gravitational waves. This black hole merger will be one of the most energetic events in the universe, briefly outshining all the stars in both galaxies combined, as measured by gravitational wave emission. Unfortunately, by the time it occurs, no humans will remain to detect it. Earth will long since have become uninhabitable due to the aging of our own star, which will enter its red giant phase and engulf the inner planets within a billion years or so. Our solar system will likely survive the merger, though its location within Milky Way is uncertain. Simulations suggest 50% chance the solar system will be pushed outward to about 3 times its current distance from the galactic center. 12% chance exists for complete ejection into intergalactic space. The remaining 38% split between staying near current radius or moving inward toward the core. If ejected, the solar system would drift through the dark space between galaxies. The night sky would transform, with no bright Milky Way band overhead, no nearby stars forming obvious constellations. The merged galaxy would appear as a distant, compact glow, along with scattered smaller local group remnants. The universe would seem emptier, darker, more lonely. The merger will take billions of years to complete, even after the first collision. The galaxies will pass through each other initially, their stars interpenetrating without actually colliding. Then gravity pulls them back together for a second pass. Multiple passages occur, each time drawing the galaxies closer. Eventually, they settle into a single merged system, but this process requires 2 to 3 billion years from first contact to final configuration. During this extended merger period, the sky will display spectacular views for any observers who might exist. The approaching galaxy will grow larger over millions of years, eventually dominating the night sky. During close passages, gravitational tidal forces will stretch both galaxies, creating long streamers of stars visible as brilliant arcs across the sky. Star formation bursts will light up colliding gas clouds, making certain regions glow brightly with the blue light of young massive stars. After merger completes, the view becomes less dramatic but stranger in some ways. The Milky Way's familiar band across the sky will be gone. Instead, stars will appear scattered more uniformly in all directions, reflecting the three-dimensional distribution in an elliptical galaxy. The overall stellar density in the solar system's neighborhood might increase, meaning more stars visible to naked eye, but they will not form the distinctive patterns we associate with constellations today. Milky Way represents the ultimate fate of our local cosmic neighborhood, assuming the collision occurs. It marks the end of an era where Andromeda and the Milky Way existed as separate entities, and the beginning of a new era dominated by a single, massive elliptical galaxy. This transformation is not unique. Throughout the universe, galaxies collide and merge continuously. The process drives galactic evolution, building larger structures from smaller ones. Looking at Andromeda today, measuring its size and properties, we are cataloging something temporary. These measurements capture a snapshot of a galaxy midlife, still growing through accretion of satellites. still forming new stars, still recognizable as a grand spiral. In several billion years, none of this will remain. The spiral structure will be destroyed. Star formation will cease. The two galaxies will have become one. Unless they miss each other, then Andromeda will continue on, and so will we, both galaxies persisting as separate entities billions of years more. The uncertainty makes every measurement of Andromeda more precious. We are documenting what might be the final epoch of a galaxy that may soon cease to exist in recognizable form. The measurements of Andromeda's true size reveal not just current reality but also future potential. This galaxy, with its 220,000 light-year disk and 2 million light-year halo, carries enough mass and momentum to reshape our entire corner of the universe. Understanding its properties helps us understand what may come, even if that future remains probability rather than certainty. We have finally measured how big Andromeda really is. The answer surprised everyone. The galaxy extends far beyond what telescopes show, reaching across half the distance between galaxies, already touching ours in ways we only recently discovered. This changes everything about how we understand our cosmic neighborhood and its ultimate destiny. The measurements continue. Each new observation refines our knowledge, constrains uncertainties, and brings us closer to knowing what the future holds. We point our telescopes at that faint smudge in the autumn sky and see not just a distant galaxy, but our cosmic fate approaching through the darkness at 110 kilometers per second. Whether collision or near miss, transformation or persistence, Andromeda will shape our future. The galaxy is already larger than we imagined, already touching us, already beginning the slow gravitational dance that may lead to merger. We stand at the threshold of understanding, finally grasping the true scale of our nearest galactic neighbor. The measurements have answered one question definitively. Andromeda is not the modest galaxy we thought it was. It is enormous, its halo extending 2 million light-years, its influence reaching across the space between galaxies. We finally know how big it really is, and now we must live with the implications of that knowledge.